For the BJT bias circuit shown, we're asked what values of RC, so this is what we were finding, in kiloohms is needed to allow the maximum possible peak-to-peak signal swing on the collector without clipping. So this is another important part right here. We are to use VCC, RB1, RB2, and RE. We can assume that to keep the transistor in the forward active region. This is also going to be important for when we use the notes linked below the like button to solve part of this. The base collector junction cannot be forward biased. That's another important part too. And then we have some more values, and we can neglect the effects of base width modulation. Our IB right here cannot equal 0 for our BJT. So we need to create a Thevenin's equivalent circuit for the base bias current because we have some voltage up here and then it's going into our ground. When we draw this out, we can basically get rid of the top left side. So we're going to have our node right here, which is our plus VCC. And then we're going to go down here, and then we're going to have our RC right here. And then underneath this, we are going to have our VC. So we're going to have VC like this, and then we can just draw it straight into our PR junction. It is an NPN. So we can go down here. This is going to be our VE. So far, it's still very similar, because we are also going to have here our RE, and then we're going to connect this right into ground. So this looks very similar so far. Well, the part that becomes different is everything after this. So with here, instead of having a resistor, we are going to have a VBB. So we can redraw this like this, because we want to have the middle part be the bias point right here. We want to bias it because it's between VCC and 0, so we have to make it. We have to make our VBB be the bias point in between it. It has to be in the middle of this. So if we continue here, we have our VBB, and then we're going to go up this way. We are going to have a combined resistance of our RB1 and our RB2. So we'll call this RBB. And then we are also going to have our VB still. So the VB will be across this right here with our RBB. So that's what that's going to look like. Now we're going to have some current flowing through here, and it's the same current that's in our picture. So we're going to have our IC like this, we are going to have our IB like this, and then we're going to have our IE like this. And that is going to be our entire circuit that we're going to look at. We can look at both of these at the same time. So the first thing that I'm going to do when we're inside of here, I'm going to say, well, we need to solve for what? Our RC, right? That's what the question is asking us for. So let's solve for our RC. RC is going to be equal to the source voltage, which is the VCC, minus the voltage at the base, which is VC, and this is all happening over our IC, so the current of our collector. Now, there's a few things that we need to find, and there's only one thing that we know. We know our VCC, so if we were to rewrite this, we could plug in the values that we know. Currently, we only know the 13 volts right here. We don't know anything else. So let's find everything else. Let's start with our IC. So we can call this step 2, where we're looking for our IC. Now, if we look at the notes linked below the like button on approximately page 103, this is where we're going to find all of our equation. Our IC is going to be equal to, we can use the equation, there's a couple different equations, but we're going to use the one where we have the alpha times our IE. And the reason why we're going to write it like this is because our alpha, we can rewrite it as beta over beta plus 1, and then we have our IE inside of here. And this is going to be equal to, well, we know our beta, it's 44, so we're going to have 44 over 45. However, we don't know our IE, right? So now we're going to solve for our IE. It's going to be in step 3. So to solve for our IE, what are we going to do? Well, there's a few equations on that page. However, they're not going to help us as much. So what we need to do instead is we need to look at our circuit diagram, and we can use the node voltage method. If we look at this part right here, in the second part of our circuit diagram, we know that our VBB, the VBB is the part that is going to be balancing this out, or not balancing it out, but it's going to be in the middle because we want to bias it, right? So that's a bias point. So we are going to set our VBB. Of course, it's going to be equal to the current times the resistance over this part, right? So it's going to be IB times our RBB. And then what else do we have? Well, we also have a base emitter somewhere in here, right? And our base emitter would be like right here. So this would be like VBE. And from our base emitter, we would be going out like this. Similarly, the voltage is going out like this from here. It's going into this node and out from there and there. So we're going to have this part, and then we have our plus VBE plus the other part. So we're adding this part, and then we need to add this part right here. And this is VE, but we can rewrite this as IE times our RE, because that's what we want to find. We want to find our IE. Well, this is a good equation, except there's one thing we should replace. This IB right here, right? We don't want to solve for IB, we want to solve for IE. So if we look at the notes again and link below the like button, we're going to take our IB and we're going to set it equal to our IC over beta. Well, we still don't have our IE here, but we know that IC is equal to alpha times our IE. So we can rewrite this again as alpha times our IE over beta. And well, alpha we know is, if we rewrite the first part, IE times beta, it's going to be beta times beta plus 1. So this beta plus 1s the betas can cancel out, and that's going to leave our IB equal to IE over beta plus 1. So now we can rewrite this entire equation, and if we rewrite it, we are going to keep our IE like this. Of course, we want to separate everything else. So our VBB is already on the left. We can subtract VBE from both sides, and then we're going to divide this by our this part and this part, because we would factor out the IE and then divide both parts. So we are going to have below here RBB over B plus 1, and then we're going to have plus RE. So that is just going to be what our equation looks like. Now we can plug in all our values. We were given VBE. Oh, we weren't given all of our values though. So if we look at this and we try to plug everything in, we won't be able to. So our IE is equal to our VBE is this negative, or the 0.7. We have a negative in front of it in our equation, so we'll just write it like this when we're filling everything in: negative 0.7 volts plus. We don't know our VBB yet, so it's going to be left blank. We have our RBB plus our B plus over B plus 1, and we can rewrite this. Our RBB is going to be equal to the following. It's going to be just our RB1 in parallel with our RB2. We mentioned this earlier. And so this entire thing, if we rewrite this, is going to be the parallel part over the beta plus 1. And for the two resistors in parallel, we're going to get 14.2435 kiloohms, and this is going to be divided over our 45. So we're going to take this and we're going to put it into our equation as 14.2435 kiloohms over 45, and our RE is going to be plus 4.5 kiloohms. Now, we don't know our VBB, so now it's only logical to solve for our VBB. So that's going to be our step 4. In our step 4, we need to set our VBB equal, we need to make an equation for it, right? Well, VBB is going to be this right here, the voltage right here, right? And if we are to write this out, we can redraw this as the voltage divider, because that's what it is. So if we redraw this, we have our VCC, right? And it's going to be drawn like this. So we have VCC here. We have our resistor value here, which is going to be our RB1, and then we have it go down here. There is resistance right here, and this is going to be our RB2, but it's also going to be our VBB. The VBB is over our RB2, and then over here is where RB1 would be with our VCC. So that's how we would write our number 4 out. VBB is going to be equal to our VCC. Inside of here, we have the voltage, or the resistance at the cross, RB2 over RB2 plus RB1. We were given our VCC and we were given our Rs, so this is simply going to turn out to be a VBB is equal to approximately 5.88 volts. So that is our VBB. And now we can plug it back inside of here. So we are going to have 5.88 volts. And so now we can solve for our IE. We are going to get that our IE is equal to, and it's just a rough approximation of 1.075 milliamps. So that is going to be the answer for that, 1.075 milliamps for our IE. And well, that means we could plug it back into here, right? So we're going to get 1.075 milliamps, and that means that our IC is equal to 1.0512 milliamps. And now we can just plug that back into our original equation as 1.0512 milliamps. However, we're not done here. In fact, I wrote this a little bit wrong. This should be VC, but not just VC. It has to be the bias point, right? Because it's we need to find it in order to allow the maximum possible peak-to-peak signal swing on the collector without clipping. So now we need to find our DC bias. It's another important part. So we can do this in step 5. Before we even get into step 5, we have some notes that we need to implement right here. To maximize the output swing at the collector without clipping, we're going to bias VC, which is the voltage of the collector, halfway between its maximum and its minimum values. These maximum and minimum values are our VCC and VB. And we're going to do this to keep it, the BHT and the BJT, in the forward active region. So we want to keep this in the forward active region, and we are just going to bias it in between VCC and VB. So that means that in step 5, we'll write this out, our VB max, our VCC, we'll just say our VC max, because the max of our collector. VC max is equal to the 13 volts, right? Because 13 volts is going into the entire system. Now, our minimum is going to be our VB, so we're going to do VC min is equal to, and this is going to be equal to our VB, which is equal to, and now we need to solve for our VB. So step 6, we'll be solving for our VB. Solving for our VB, we're going to set our VB equal to, well, if we look at the original circuit, we have our node right here that's perfectly laid out. VB is going to be equal to, and then it's also important to look at this as well. We have our VBB, so the entire voltage here, minus the IB times RB, because that is the voltage that's getting lost over here. So we can delete those lines also, so it's a little bit clearer to see. We are going to have the minus IB times our RB, and this is going to be equal to our VBB we found previously to be 5.8 volts, or 88 volts. And then our IB and RB we also found, and our IB we found in the equation right here, 1.05 or 75 milliamps divided by our beta plus 1, which is 45, and then we are going to multiply this by the resistance value, and the resistance value is a 14 because it is RB, and our RB is the value right here. It's not RB, it should be RBB, so that should be fixed right there, RBB, and our RBB again, we found this resistance value right here, so it's going to be 14.2, and then we'll just do dot 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 because I'm running out of room. And so we're going to plug all of this into a calculator, and once we plug this into a calculator, we are going to get that our VB is equal to 5.54 volts. So that's going to be our VB, and then we can plug this in right here, 5.54 volts, right? So we're going to take our maximum and our minimum, and this will be step 7, and what we're going to want to do is just subtract them. So we're going to do VC bias is equal to 9.27, and we'll just have a subtraction symbol right there for step 7. So that means we're just going to come back up to our original equation and minus a 9.27 volts. And so when we rewrite this out, we are going to get that our RC is equal to 3.55 kiloohms. And that is going to be the answer to this problem and how we would go about solving it and anything like this. If you have a different value, you could just plug them in. If the circuit's a little bit different, you could just modify this based on that as well.